This is the Masking Handbook for Audiometry. In this video, we'll be looking at how to identify overmasking. Here's a sketch showing a possible overmasking situation. The left ear is the test ear in this case, while the right ear would be the non-test ear. So the right ear is the ear into which would be delivering the masking. Overmasking is more likely to occur when the air conduction hearing of the non-test ear is poor, while the bone conduction hearing of the test ear is pretty good. When the air conduction hearing of the non-test ear is poor, the masking noise must be loud in order to have a masking effect, and a louder level of noise increases the risk of masking noise crossover to the test ear. You can see the colored sections there showing potential masking levels. We have the blue bar showing the masking noise must be as loud as the hearing threshold. They're at 500 Hertz. The yellow bar shows compensation for occlusion effect. The pink bar shows some active masking. In this case, it's 10 dB. And then the cross-hatched section shows potential increases in masking due to plateauing. So you can see the level that's proposed ultimately for this right ear at 500 Hertz ends up being 95 dB. At that high intensity level, it's quite likely that the masking noise will cross over to the left ear, where it could potentially affect the hearing at 500 Hertz on that side. Let's reconstruct the situation here. We're dealing with a left test ear that has really good cochlear bone conduction hearing. The non-test ear has poor hearing. We'll construct our initial masking level, and you can see the compensations that we mentioned in the previous slide. We can infer a situational intraoral attenuation value, or a SIT-IA value, of 55 dB due to the air conduction threshold in the right ear at 500 Hertz relative to the bone conduction threshold, which is unmasked. The real IA may be greater than that. We don't know. We assume it's possible that 25 dB of masking noise could cross from the non-test ear. If that were the case, we'd be overmasking because the 25 dB of potentially cross noise would mask the cochlea of the left ear quite easily if the bone conduction hearing was 0 dB on the left ear side. Things to consider when looking for a possible overmasking situation: the non-test ear air conduction hearing is poor, when the bone conduction hearing of the test ear may be pretty good. Overmasking will not occur using the optimized method. In the optimized method would always be masking the better ear, and the optimized method is designed to provide high levels of masking that will avoid overmasking. So if you have a situation where you're using the optimized method either for air or bone conduction testing, that means the poor ear will be the test ear, and just by definition the optimized method will avoid overmasking. So really you'll be on the lookout for potential overmasking when using the plateau method. Let's take a look at our plateau graph. The x-axis along the base represents masking levels. The y-axis, the hearing threshold levels that are measured. We see the blue plateau region is stable when introducing masking levels from 40 to 80 dB. The stable responses represent valid mask thresholds when the hearing threshold level is at 45 dB. Because it's on the plateau, the hearing threshold measurements are guaranteed to be coming from the test ear. Stable hearing in the presence of increasing masking to the non-test ear confirms responses from the test ear. We have two other areas on the graph, the gray and green ranges, that show changing, that is, increasing hearing thresholds as the masking noise is increased. These two ranges do not represent valid hearing thresholds of the test ear. Undermasking can occur at lower levels of masking noise. The green region is showing increases in responses as well, with masking noise increases. The green region illustrates quite loud levels of masking noise and represents noise that is so loud it's crossing to the opposite test ear side and actually interfering with our attempts to measure the hearing from the test ear. This is the overmasking range. So it's important to be observant of hearing threshold shifts as masking noise levels are increased. It means you don't have a valid hearing threshold measure yet. You can then estimate if it's due to undermasking or overmasking. 3 points to consider. There's less risk of overmasking when using low intensity masking levels. Higher risk of overmasking when using high-intensity masking levels. We should be aware of our min-IA or SIT-IA values when assessing the risk situation. The SIT-IA can sometimes be inferred and used based on specific audiometric situations. The min-IA values are the values that we use from the literature on intraoral attenuation. We can assess the risk of overmasking mathematically as well. The risk of overmasking checks the potential crossed level of masking noise and compares it to the cochlear hearing of the test ear. So if the potential crossed level of masking noise is greater than the cochlear hearing of the test ear, then there is a risk of overmasking. The potential value of crossed mask noise is determined by subtracting the intraoral attenuation value from the level of the masking noise that is being delivered. Let's look at this situation. We have some hearing loss in both ears and an unmasked bone line, which is great, but we don't know which ear those bone conduction results are coming from. The left ear is our test ear. We'll add a bit of masking noise above the 500 Hz threshold in the right ear, a total effective masking level of 45 dB. We do have an air bone gap of 40 at 500 Hz. If we compare the air conduction result from the left ear to the unmasked bone threshold. So we could infer a SIT-IA value of 40 dB. If we consider our min-IA values, however, we see the min-IA from the literature is 50. So we'll go with this value as it's the minimum known possible attenuation value for that situation. In general, we'll accept the higher value, whether it be the min-IA or SIT-IA. So we can infer also that the 40 dB hearing threshold level from the left ear is accurate, and it's not due to crossover to the right side. Let's plug our numbers into the formula. We'll quantify our risk of crossover by entering our masker level and our IA value, in this case the min-IA. We'll come up with a -5 dB value, and we'll compare this to the cochlear hearing of the left test ear, which is 0 dB. We use the best bone value taken from the unmasked bone conduction response. In this case, the -5 dB value is not greater than the cochlear hearing, presumably from the left ear, so there is no risk of overmasking. Let's look at a different situation. The same unmasked bone conduction results, but the hearing is worse in both ears. By comparing the unmasked air conduction results at 500 Hz from the right ear to the bone conduction threshold, we can infer a SIT-IA value of 55 dB. This is higher than the min-IA, so we can use this. And we have a masking level of 75 dB. If we plug our numbers in, we'll come up with a 20 dB risk of crossover compared to the possible 0 dB cochlear hearing that could be coming from the left ear. This is a positive risk of overmasking situation. Third scenario now, same level of masking, same air conduction hearing on the right side. The unmasked bone line is different this time. However, let's take a look. We'll use the min-IA value of 50 dB this time because the inferred SIT-IA is well below this min-IA value. Our cochlear hearing has changed though. It's now at 25 dB. The risk of masking crossover is 25 dB, and that is not greater than the cochlear hearing estimate. In this scenario then, there is no risk of overmasking. Again, there's less risk of overmasking when using low intensity masking levels. Threshold shifts with high levels of masking may be due to overmasking. Another method is to determine a potential maximum masking level. If the possible masking level exceeds this value, then there is a potential risk of overmasking. Let's look at 500 Hz here. We'll be looking at masking the right ear. So the left ear is the test ear, and we have a unmasked bone conduction threshold of 10 dB. We have our 50 dB min-IA value for inserts. We know the masking level can go at least up to this level. Since 50 dB IA guarantees that masking noise would remain with our non-test ear up to that point. But we also have the test ear bone conduction value to consider. A max mask determination Depends on whether the test ear could hear a cross-masking noise from the non-test ear. There's a big difference between the test ear having bone conduction hearing of 0 compared to 30 dB. The max mask value incorporates the bone conduction hearing of the test ear, or an inferred bone conduction threshold of the test ear, into its formula. In this case, we'll use the unmasked bone conduction threshold of 10 dB, since we don't know the left ear bone conduction thresholds yet. We'll go with the best bone results available. This gives us a max mask value of 60 dB. In formulaic terms, the theoretical max mask value equals the IA of the earphone and frequency added to the bone conduction hearing of the test ear. If your masking level exceeds this theoretical value, you're entering a situation where overmasking becomes possible. This is the Masking Handbook for Audiometry. If you liked this video, you'll love the handbook. For more resources on masking and to learn how to purchase the book, check out maskinghandbook.com.